I'm Jemima. I'm a PhD student at ANU working with Callum and Andy. So today I'll be talking about some aspect of my PhD work. So it's not directly related to the Southern Ocean, but hopefully I'll be talking about a few of the processes or dynamics that we can see in the North Pacific that is also applicable in the Southern Ocean. The talk is on the identification and propagation of near-inertial internal waves, and maybe has talked a bit about near-inertial waves previously, but I'll just start by discussing how near-inertial waves are formed. So essentially, when you have like a wind stress blowing on top of the ocean surface, it resonantly forces inertial motion in the mixed layer. So up here, you have inertial motions being generated, and these inertial motions are essentially associated with areas of divergence and convergence, which in turn cause vertical velocity at the base of a mixed layer. So essentially, those inertial motion in the mixed layer kind of cause the Ekman pumping at the base of the mixed layer that goes up and down. And this kind of acts as an oscillator that in turn causes the radiation of near inertial waves into the interior of the ocean. So why do we care about near inertial internal waves? Well, if you look at the overall group of internal waves, near inertial waves are kind of estimated to contain 50% of the overall internal wave energy. They tend to propagate as internal tide where they get generated at the source. They tend to propagate to the far field. They propagate long distances before breaking or causing mixing and turbulence. So essentially, you have this far field. They contribute to the far field mixing. And finally, they have strong vertical shear, so they are a major contributor to turbulence. So because of all those properties, near inertial waves can contribute to mixing and in turn drive or maintain the abyssal stratification. So this is more or less why we care about near inertial waves. Since we know that these waves can contribute to mixing, we're interested in how much mixing can they cause, and indirectly, if we can quantify or estimate the amount of energy they have, we can also estimate the amount of mixing or turbulence they can cause. So I'll also go back to how we define or how we identify internal waves in general. So here we have, if we look in like the Fourier space, or if you look at the frequency spectrum, any motion that has a frequency less than f is considered as a balanced geostrophic motion. So these are like vortices and jets, and any motion that has a frequency above f, and I think Matt also touched upon this, is considered as an internal wave. So if we look at the internal waves we're interested in this talk, we're interested in the near inertial waves. And as the name says it, these internal waves have a frequency near f. So typically we define these internal waves as having a frequency between 0.9 and 1.1 f. The definition kind of varies across different studies, but essentially what we're trying to do is get this inertial peak here, which is kind of defined where the near inertial waves lie. So because the near inertial waves kind of lie near this frequency cutoff between geostrophic motions and internal waves, the background flow can influence the way we define or identify near inertial waves. So one of the ways the background flow can influence near inertial wave is through the background relative vorticity, which is essentially when you have a bunch of eddies or when you have a mesoscale vorticity. So one of the ways the eddies can influence near inertial waves is that I previously talked about how they get generated. So when they get generated, when the wind blows over, it causes inertial motions which then tend to radiate near inertial waves and these near inertial waves have a frequency near F. However, when you have eddies, when you have strong eddies present, they tend to shift this frequency from F to F effective. So if you have a negative relative vorticity, so an anticyclonic eddy, I'm talking Northern Hemisphere here. So if you have a negative vorticity, the frequency where the near inertial waves can exist will be at F effective, which is essentially lower than F. So in a negative relative vorticity, F effective is less than F, and in a positive relative vorticity, F effective is slightly larger than F. So what essentially happens is if we look back at this frequency spectrum where we were looking at how the near inertial waves are defined, when you have negative vorticity, this frequency bandwidth will kind of broaden because, again, we're not looking at F, but we're looking at the F effective. Whereas if you have positive relative vorticity, the frequency bandwidth over which the near inertial waves can exist will be narrowed. Yeah, and something else I wanted to quickly touch up on is when you have near inertial waves, you have a phenomenon which is called the inertial trapping. Because in negative vorticity, your F effective is less than F. Any near inertial waves that gets generated in a negative vorticity eddy would tend to get trapped, again, because internal waves can only exist between F and N, or if you're in a negative vorticity between F effective and N. So because the F effective here is lower than F, any near inertial waves that gets triggered in a negative vorticity we tend to get trapped and won't be able to propagate away. A second way in which our definition or our identification of near inertial waves can change is when you have a strong background flow. So this is related to the Doppler shift. The Doppler shift is essentially when the intrinsic frequency gets shifted by a background current. So here, omega naught is the Eulerian frequency. So it's the frequency that you get when you're at a fixed position, whereas the intrinsic frequency of a Lagrangian frequency is the frequency that you get or that you measure when you move with your background flow. So again, if you have a frequency spectrum, if you have a strong background flow, if you don't have any background flow at all, this term here, your Doppler shift, will be really small. Your Eulerian frequency will be more or less like your intrinsic or your Lagrangian frequency. Whereas if you have a strong Doppler shift, whatever you measure in the Eulerian frame will be shifted relative to your Lagrangian frame. I also forgot to say, if you have any questions, just stop me at any point or ask at the end. I'm happy with that. So the reason I'm talking about those Eulerian frame versus Lagrangian frame is essentially when you're filtering out internal waves. So when I was talking about this, where you're like trying to filter out your internal wave, you need to look at the intrinsic frequency. So essentially the frequency that you get on a Lagrangian frame. But usually when people, especially when you're using observational data set, or even when you run a numerical simulation, when people will try to filter out their near inertial wave, they would do it on a Eulerian frame, which is fine if you don't have a strong Doppler shift. But as soon as you get a strong Doppler shift, your observed Eulerian frequency will be shifted from your intrinsic Lagrangian frequency. So the shift would also depend on which direction the waves are propagating with respect to your background flow. So we essentially wanted to investigate those two effects. So we've seen how the background vorticity affects the frequency cutoff. So essentially how you can, the lower frequency of your near inertial waves. And we've also seen how the background flow can affect the way you plot out your frequency spectrum. And we wanted to see how those two effects kind of influence the identification of the near inertial wave. So what we did is we ran a realistic numerical simulation. Our domain is in the North Pacific near the extension of the Kuroshio. And the reason why we picked that study region is because you have a strong background flow. So in terms of the extension of the Kuroshio, you have a strong background flow here. And you also have a strong mesoscale eddy field. What we did is we forced at the boundaries, we had hourly winds, and we also picked a time period where we had like a small storm system. So the wind associated with storm systems likely generate near inertial waves. And we made sure we analyzed a period. So this is the wind, this panel here shows the wind work. And we made sure that we were analyzing data following the passage of this small storm. So this upper panel here shows the Rossby number, which is related to the background relative vorticity. So we had a bunch of anticyclonic and cyclonic eddies to make sure that we capture this phenomenon where the inertial frequency get shifted to the effective frequency, to the effective frequency, and also cyclonic eddies where you have positive relative vorticity, where your F effective is larger than F. The lower panel here shows a proxy for your Doppler shift. So essentially where you get the purple color here, you have strong Doppler shift. So in this region, your frequency spectrum in a Eulerian and a Lagrangian frame will be different. So we ran our model and we analyze the fields that we get from our numerical simulation. And what we try to do is from the total field, we try to extract the near inertial wave. So you do that in the Fourier spectrum. So essentially, you put it in a Fourier space, you filter out your near inertial waves depending on your from 0.9 to 1.1 F, and then you do an inverse to get back your wave component. But what we did is we had four different types of filters to extract out our near inertial waves. So I'll talk about the first two. So we did the filtering on a Eulerian frame, but here the subscript is the frequency cutoff that we use. So those two are on a Eulerian frame, but the first one is using a frequency cutoff at F, which means that we're not including the effect of a relative vorticity. The second one is still on a Eulerian frame, but using a frequency cutoff at F effective. So here we are including the effects of a relative vorticity. And then the next two filters are run on a Lagrangian frame. So on a Lagrangian frame, you're essentially following the background flow and you're including that Doppler shift effect. And so the third one is on a Lagrangian frame, but using a frequency cutoff at F. So essentially, we are including the Doppler shift, but not the relative background vorticity. And then finally, our fourth filter is on a Lagrangian frame, but using a frequency cutoff at the F effective. So here, this last filter contains both the effect of a relative vorticity and the Doppler shift effect. So essentially what we're saying is that this filter correctly identifies our near inertial waves because it both includes the Doppler shift effect and the relative vorticity. So we essentially have four sets of filters to filter out our near inertial waves. And we end up with four sets of filtered values of U and V for our near inertial waves. And what we do next is we compute four different sets of kinetic energy. And we essentially say the kinetic energy that we compute from the filtered fields are related to the near inertial wave energy. but each set of kinetic energy either includes or neglects the effect of a vorticity and the Doppler shift. So what we did is we defined 3 biases. And so the biases are essentially percentage errors. And what we're doing is essentially comparing. So we essentially say those 3 are apparent wave energy because they are missing one or both effects, whereas the 4th one is our true, gives us our true wave energy because it includes both effects. And then, so we compare different pairs. And so just to point out here, the zeta bias is the bias or the error in wave energy that you get when you omit the relative background vorticity effect. The sigma effect is the wave energy bias that you get when you omit the Doppler shift effect. And this last term, zeta sigma bias, is the error in the wave energy that you get when you neglect both effects. So first, we'll look at what happens when we ignore the background vorticity in our identification or in our wave filtering. So as expected, so the dashed black line here represent the anticyclonic eddies, so negative vorticity. So if we neglect the background vorticity, we're essentially underestimating energy. We're underestimating wave energy because essentially, as we've seen before, in negative vorticity, you get a broadening of your frequency bandwidth. And when we don't include the background vorticity, we don't really capture that broadening, which is why we end up with an underestimation of energy in negative vorticity. And we can see this is the kinetic energy power spectrum. This is the kinetic energy power spectrum in anticyclonic regions. And we can see that if you include the F effective in your frequency cutoff, the frequency bandwidth is essentially broader. And the opposite happened in cyclonic region. Energy is essentially overestimated because we're not capturing that narrower frequency bandwidth when we are ignoring the background vorticity effect. And then this is the bias that we get when we ignore the Doppler shift. And again, you can see if you compare the frequency spectrum on a Lagrangian versus a Eulerian frame, you can see the shift in the frequency spectrum. And this is, so I forgot to say, the frequency spectrum that you see here are averaged for the anticyclonic region, averaged in those black dashed line, and in the cyclonic region, they're averaged in the green contour. For the Doppler shift, the frequency spectrum is averaged in the high Doppler shift area, so in the extension of the Kuroshio. And then this is kind of our control. So when you don't have a strong relative background vorticity, or when you don't have a strong background flow, essentially no matter which filter you use, the frequency spectrum is more or less the same. And then the last panel here is the bias that you get when you ignore both the relative background vorticity and the Doppler shift effect. So I forgot to mention all those are averaged over 3 days, and this is at 200 meters. And what we did is we computed all those biases at different time and at different depth. And then we binned them as per values of a relative vorticity here, which is a Rossby number down here, and as per the Doppler shift. So as expected, in negative vorticity, the wave energy is underestimated. And in positive vorticity, the wave energy is overestimated. And finally, I will quickly talk about, so previously we were looking at the kinetic energy of a wave. And here what I've plotted out is the wave horizontal flux. So again, to get the wave horizontal flux, you essentially multiply the horizontal velocity of the wave times the pressure field of the wave. So again, we had the different set of filtered values of U and P, and we computed the wave horizontal flux when you don't include the relative background vorticity nor the Doppler shift in your filter. So the quivers here represent the horizontal wave propagation, and the color represent the background zonal speed. So if you look here, when we don't include the background vorticity nor the Doppler shift, the waves, there's not really a directionality to the wave propagation. Whereas in the filter where we include both the relative background vorticity and the Doppler shift, there's a certain directionality to the waves. So if you look at the quivers or the arrows, the waves are essentially propagating in the opposite direction to your background flow. And this can be explained, so this is only captured when you include both effects in the filtering of your waves. And this can also be, the dynamics of it is because the intrinsic frequency adjusts to the Doppler shift and changes with the background flow. So I won't go too much into details, but essentially it's only the Lagrangian filtering, or when you're filtering the waves on your Lagrangian frame, that you can get this directionality in your wave propagation. So just some key points. The background flow is essential in quantifying the near inertial wave energy. So when the background flow and when the background relative vorticity and the Doppler shifts are neglected from the identification of a near inertial waves, the near inertial energy is underestimated by 40% in anticyclonic structures and can be overestimated by 100% in cyclonic flows. The background flow, again, the background relative vorticity and the Doppler shift are essential in correctly identifying the near inertial wave propagation. So this selective propagation or unidirectional propagation of near inertial wave in jets is only revealed when we account for the Doppler shift in our wave filter. So how is this all applicable to the Southern Ocean? Well, this panel here shows, it's a figure I've borrowed from Liu et al. 2019, and it shows the wind work. And I think from all the previous talks we've listened to, we know that the Southern Ocean is a region where you have strong wind work and where you can get strong inertial motions and strong near inertial waves being generated. And also, this is a figure from Wallen et al. So the top panel here shows the average eddy kinetic energy. So we were looking at the North Pacific, which is kind of near a western boundary current, where you have a strong eddy field, where you have a strong background flow, but you also get strong background flows and strong eddy fields in the Southern Ocean. And this bottom panel here shows the near inertial energy flux from the wind, which is also strong in the Southern Ocean. So based on what I've been discussing, we have seen this strong interaction between the background flow in terms of the eddies and in terms of the flow itself. And we've seen this strong interaction with the near inertial waves. And the Southern Ocean is kind of a hotspot and a region where you get strong eddy kinetic energy and strong near inertial motion or near inertial waves. So moving forward, it will be good to, yes, look at near inertial waves, but also consider the background flow in the identification and definition of near inertial waves. Thank you.